Let's take a look at example 4. All right, we're going to do this one, and we'll talk about it. We're going to do 2 examples here, and this should help you do the last question on this particular assignment. Let's just start with this. So we have y equals 5 to the x power. We're finding the derivative, dy dx. All right. Now, see, the thing that a lot of people want to do is say, well, look, the derivative of 5 to the x is 5 to the x, just like this. That rule is only true when the base is e, which is 2.718, and so forth. This rule does not generalize to other bases, such as 5. This only works when it's e to that power. So, no, that rule does not apply to this question. So what we're about to do is what we call logarithmic differentiation, and we will do 2 examples of this. We do logarithmic differentiation when we have the variable as part of an exponent. X is part of a power, all right? So here's the trick that a very wise person came up with at one point in math history. This person said, what if we applied a natural log to both sides of that equation? And I think you'll see why here in a minute as to why this was a pretty ingenious thing. So notice we apply natural log to both sides. Now, what good does that do? Well, here's what it does. Whoever thought about this was thinking a step ahead, and they said, you know what? Once you apply a natural log to both sides, can't we then, because this side became natural log of something to a power, doesn't that enable us to apply this algebra property, which was in existence before this technique was invented? Can't we now bring that power down in front, and instead of being a power, isn't that x now a coefficient, a multiplier? And that makes this much more conducive to calculus. And so, moving forward from here, now we can differentiate both sides of this thing with respect to x. Ow, all right? Now, this is where we do that implicit differentiation, which was a long time ago. But if we differentiate both sides with respect to x, and here we go, chain, natural log, that'd be 1 over y. That's the derivative rule for natural log, right, of something. And then the derivative of what's inside. And if you differentiate y with respect to x, that gives us the dy dx that we've seen. So this side becomes 1 over y dy dx. Doing the chain rule, outside, inside, again with respect to x. Now the other side's a little bit tricky, because what we need to realize over here, and we're going to do 2 examples, so if this one doesn't click, we'll do one more. What you got to remember is that the natural log of 5 is actually a number. It's a coefficient. You can grab your calculator and type in natural log of 5, right? Natural log of 5. I don't know if you can see it or whatever, but that's like 1.6 blah blah crazy number. So what we have to realize is this is just a number times x. And isn't the derivative of a number times x simply that number? Just like the derivative of 8x is 8, and things like that. Okay, last thing. The question was to find dy dx. So we treat this like an algebra question, and we say, I want dy dx by itself. I want to get rid of the 1 over y. How do you get rid of 1 over y? You multiply it by y to clear the fraction. So you multiply by y. And you think, well, then we'll multiply the other side by y. But here's another part of the ingenuity of this. We were told at the beginning of this question that y was equal to 5 to the x power. So we're going to multiply the left-hand side by y, and we're going to multiply the right by what y is equal to at the beginning of the question, otherwise known as 5 to the x power. These cancel and leaves dy dx, and we're left with the natural log of 5 times 5 to the x. And again, note that doesn't really follow that rule. This easy rule back here only works when the base is e. So if it's anything other than that, this would be the technique to get your derivative. And there's patterns you could memorize if you wanted, but we're not going to go there. All right, now here's the deal. I was looking at these remaining examples, and then I was comparing them to homework, and I kind of came to the conclusion that those two examples, even though they could help you do the homework, I'm going to do you a favor. I'm going to make up a question that would resemble the last question on this particular assignment. So keep in mind, this is being done on purpose. Instead of working these two, I'm just going to make up one that would be extremely similar to your homework. So I'm making this one up on the spot. Let's say we had y equals 9x squared plus 7x minus 3 raised to the 2x minus 5 power. Look at that. We got x's on the ground as well as up in the air. And this would be very similar to your last question on this particular assignment. So again, this is being done on purpose. We're not working these. I just made one up to resemble your homework. Now the thing that would hopefully trigger in your head, you're going to do logarithmic differentiation, is that the variable x is part of our exponent up here. It's up in the air. We got x's on the ground and up in the air. What? So this would be the point where you would do logarithmic differentiation, and therefore we apply a natural log to both sides of that original equation. I don't know, every time I see this I think, how ingenious. Because this person was obviously thinking ahead when they thought, what would happen if we applied natural log to both sides? Well, the left-hand side would remain natural log y, but the right-hand side, and this again is where I think the ingenuity came into play, this person goes, you know what? If you apply a natural log over there, you're going to have something to a power. And the properties of algebra allow you to bring that power down in front. So this now allows us to change this into 2x minus 5, bring it down in front, natural log, da-da-da. Wow, how ingenious was that? What that did is that this person must have thought, how am I going to get that thing on the ground? Oh, if I do a natural log, the properties of algebra let me bring it down. And you know what this the right-hand side becomes? It's a product now. And we have a rule for that, product rule. Yay! All right, so moving on, if the goal is to find dy dx, we will now differentiate both sides with respect to x. Okay, so over here, chain. What's the derivative for natural log of something? 1 over something. And that's the derivative for natural log. And then, when you differentiate y with respect to x, ouch, that'll be dy dx. See, that's how you get the dy dx into the discussion. And then the right-hand side would be to differentiate this with respect to x, which, as mentioned a minute ago, would be the product rule. We have two factors here. We have the 2x minus 5 being multiplied with this thing here. And so here we go. We've already differentiated this side with respect to x. Now let's do the same thing over there. So we will have the first times the derivative of the second. I can tell I'm starting to run out of room, but we'll make it work. Let's see, the derivative of this, we practiced that on some previous slides. Natural log of expression. Chain. 1 over the expression times the derivative of what's inside, 18x plus 7 minus 0. This is just like the questions we saw earlier where we found the derivatives of things of this type. And that would be the derivative of that. Plus, I'm going to work down because if I keep going this way, I'm going to go off screen and disappear forever. Where did he go? Here I am. Let's see, the derivative of this would be just 2. And then natural log already had a term being a derivative. So the point is differentiating this right-hand side would be very similar to the ones that we were practicing on previous slides. And yes, there's lots of steps here. But look, you guys have proven to me time and again, you understand process. where we have trouble, and you are not the only people in the world, we all have trouble with mechanical things, and it'll happen. Okay, now, we're almost done. We don't want 1 over y dy dx, we just want dy dx. So, just like the question we saw earlier, you get rid of 1 over y by multiplying by y. You can do that over here, and that'll clear it out, won't it? And then you're going to multiply this entire other side as a quantity. Let's put a big old grouping symbol around it. And we're going to multiply it by the expression that we were told was equal to y at the beginning of the question. We are effectively multiplying both sides by the same thing, if indeed those two expressions are equal. So the other side gets multiplied by, I hope it fits here, and put a big old grouping symbol around it, 9x squared plus 7x minus 3 all to the 2x minus 5 power. I hope that fit. Yay. All right. And I don't have room to keep writing it, but hopefully you look at this side and go, you know, the y and the 1 over y, that's a step here. But the final answer would be to go, those cancel each other, and dy dx equals that. Woo! All right. Isn't that impressive looking? I mean, that really is awesome. So why don't y'all come up here, let's get a picture of this together. People say, hey, what'd you guys do today? Here, everybody get in. All right, come on. All right, ready? Everybody smile. Isn't that awesome looking? Look at that. Look at what we just did. You guys will get to do one of these at the end of that assignment. So I believe that will indeed wrap up assignment 36-37. And I want to point out that that was the differentiation side of things when you have e and logs. Differentiation. So assignment 36-37 involves all the differentiation that we just did. Now, we're going to continue with the same series of examples, and then assignment 38-39 will be how do you integrate exponentials and logarithmics. Can't wait for that, huh?